Welcome class. Today, under the heading Mechanical Properties of Bulk Matter, we are going to discuss the behavior of solids. And the topics to be covered are elastic behavior of solids, then stress, thereafter strain, and finally Hooke's law. The objectives behind discussing or learning these above topics are observation from our day-to-day life experiences. We will be able to understand what is elastic behavior of solids. Secondly, comprehension. The knowledge of elastic behavior or elasticity of solids will be known to us. Thirdly, understanding. We will be able to understand the behavior of solids, why they behave so, on the basis of microscopic nature of the solids, their microscopic picture, atomic or molecular picture of the solids. And finally, when we will learn all these things, we will be apply to this knowledge to the different practical purposes in our day-to-day life. We will be able to understand and apply the elastic behavior of substances on the basis of how elastic they are, means more elastic, less elastic, perfectly plastic. On the basis of that, we will be able to use them in our day-to-day life. Now let us learn about the elastic behavior of solids. So first, see this picture, this figure 1. In the figure 1, the first spring is hanged, suspended from a rigid support but unattached with a load. So it has a length capital L, original length. Now in the second spring, a load is attached to it, that is a weight, and it is deforming force. Why it is deforming force? Because it is increasing the length of the spring. Now when this load is removed, again we notice from our common experience that the spring regain its original position. So why this happens? Because this spring is applying an internal restoring force in upward direction in response to this deforming force, which is the weight. Internally, this spring is applying force. Also, we have felt the same when during exercise we use bull worker. We stretch and compress it. We feel force opposite to the force we have applied on the bull worker. Now come to this figure number 2. Now this is, here we have understand the action of one spring. Now here are a large number of springs, and this is a spring ball system. The balls are held regularly by these springs. So if we try to increase the size of this spring ball system, what will happen? These springs which are binding these balls, they will try to bring back the system to the original configuration. Now we are going to extend our common experience of this ball spring system to understand the microscopic picture of solids. So a solid is composed of atoms or molecules, where each atom or molecule is surrounded by other atoms or molecules. Now one atom or molecule is surrounded by several molecules. This atom is surrounded by these molecules. These atoms or molecules are bounded together by interatomic or intermolecular forces and stay in stable equilibrium position. So these molecules or atoms are at equilibrium position, different lattice points, because of the interatomic or intermolecular forces existing between these atoms or molecules. This can be imagined by taking a model of a spring ball system. Here the balls represent the atoms or molecules, and the springs the interatomic or intermolecular forces. Now these balls are representing atoms or molecules, and these small springs are representing the interatomic and intermolecular forces. Now recall that we have learned in junior classes, interatomic or intermolecular forces are electrical in nature. They may be attractive, they may be repulsive. Now, in this system, if any ball is displaced from its equilibrium position, either compressed or stressed, either the distance between them is increased or decreased. If we disturb any of these molecules or balls from the system, what will happen? Now, recall that just we discussed that these balls or the atoms will try to bring the system in its original configuration, and as soon the deforming force is the stretching force outward is removed or the compression force is removed, the system will come into its original configuration. So if any of the ball is displaced from its equilibrium position, either compressed or stressed, the restoring force of the spring comes into play and brings the ball back to its original position. This accounts for the elastic behavior of the solids. Let us now clear some or understand some concepts on the basis of just we have discussed. First is elasticity, the property of a solid body by virtue of which it tends to regain its original size and shape when applied force is removed. Applied deforming force is removed is called elasticity. Second concept is deforming force, a force which when applied changes shape or size or both configuration of the solid body. Just in the case of a spring, the load was the deforming force, the weight of the substance was the deforming force. Now next concept is perfectly elastic body, a body which regains its original configuration immediately and completely after removal of deforming force is called perfectly elastic body. Now here we have termed it as immediately and completely. The body should come to the original configuration immediately and completely. If this happens, then the body is perfectly elastic body. The near examples of the perfectly elastic bodies are quartz, phosphor, bronze, etc. Next is perfectly elastic body. Now this is just opposite to the perfectly elastic body. A body which does not regain its original configuration at all on the removal of the deforming force is called perfectly elastic body. Means it does not regain its original configuration on removal of the external deforming force. Example, putty we apply before painting the walls of our houses, buildings. Mud Paraffin waxes. Paraffin wax are some of the examples from our daily life. Can you cite more examples? Now another concept, important concept is stress. The internal restoring force acting per unit area of the deformed body is called stress. Now, recall this is internal restoring force. The spring was applying in response to external load or weight, or the interatomic or intermolecular forces were applying in response to compression or stretching. So stress is restoring force per unit area, restoring force upon area. So the SI unit of it is Newton per meter square or Pascal. Dimension is ml minus 1 t minus 2. Now tell me whose dimension and unit is same as that of the stress. This is assignment for you, and how they are different. Next concept is strain. The ratio of change in configuration to the original configuration is called strain. Strain is change in configuration upon original configuration. Means same configuration is taken here. If this is change in length, then this is original length. If there is change in area, this is original area of the surface. If this is change in volume, this is original volume of the body. If this is arc, means some deformation in the form of angle, this is arc, then this will be radius. So same configuration is in the numerator and denominator. So it is, since it is ratio of the two like quantities, therefore has no units and dimension. This is a unitless and dimensionless quantity strain. Now next important law is Hooke's law, and this is very important law. Within elastic limit. Within elastic limit means the limit up to which the solids regain exactly its original configuration. So within elastic limit, stress is directly proportional to strain. That is, stress is proportional to strain. Now we know that to remove the sign of proportionality, we put a constant, and here the constant is modulus of elasticity. So stress is equal to modulus of elasticity into strain. Therefore, modulus of elasticity is stress upon strain. Its SI unit is Newton per meter square or Pascal, and dimension is ml minus 1 t minus 2. Now just recall that the dimension of this modulus of elasticity and unit are same as that of the stress, because strain is a dimensionless quantity. So now tell me, what are the different physical quantities having same dimension, same unit, but they are different?